All right, good morning, everyone. It is 10 o'clock, so let's get this thing started. I'd just like to start off by seeing if those of you that that are familiar with this layout, if anyone could just throw us a little chat in the questions bar, just to make sure that everyone can hear us just fine. I'd really appreciate that. I see one person had written something. I see it says, okay, good. If anyone else could throw a little question in there. All right, great. Thank you. All right, so good morning again. Thanks for joining us for another Rath Associates PDH webinar. Many of you have been to our last 20-minute webinar episode on essentially the same topic. When advertising that presentation, many of you asked if we could roll this out as a full-on PDH course. So we did. So we are. This episode is called Optimizing Condensing Boiler Plant Efficiencies. We'll be going much deeper and review the various factors that can influence the efficiency of a boiler or water heater. And by the way, we're going to use the term boiler often, just so you know, but we mean it as either boiler or water heater. We hope to get people to understand today that the efficiency printed on a unit's brochure does not mean that's the efficiency you're going to get. High turndown does not automatically mean high efficiency, although many would love to make you believe that. And we also are going to review the many other factors that can promote high efficient operation. It is not just important because it can save people money and because it's the green thing to do, but in about 4 years from now, the new Local Law 97 is going to be in effect, which is essentially a tax that building owners are going to have to pay if their carbon footprint is above a certain threshold. And in 2030, the rules are going to be way more strict. And they predict that only 20% of buildings in existence today are going to comply with the 2030 guidelines. So we really have to start designing with the 2030 guidelines in mind today. So this is a PDH course worth 1 credit, and we're going to distribute the certificates within about a week or two. I know many of you guys are probably waiting for the BPE one. I promise it's coming soon. So just bear with us. We're trying to get things coordinated with the people with the Practicing Institute of Engineering. So with this COVID thing, everyone's been a little bit kind of thrown off, but we're getting that thing moving along very soon. Today, we're going to have the pleasure again of having Dr. Lou Vorseveld from Laars Heating Systems to give the presentation. Dr. Lou's got 25 years experience in the North American market in the boiler and volume water heater industry at a variety of engineering, GM, and sales positions. He's worked for both the European and North America-based boiler manufacturers covering residential and commercial boilers and water heaters in both the condensing and non-condensing arenas. He's earned his BS, MS, and PhD from the University of Vermont with a concentration in thermal sciences and combustion. So yeah, he's pretty much the go-to guy on this topic. For those of you that are new to the GoToWebinar platform, this is what your screen looks like. The 2 most important buttons are the question button and the handouts button. You see them, let's see if I can use my mouse. You see them up here, questions and handouts. Please, everyone, I'd like you to go to that questions bar. You might remember I asked this last time. Go there right now. I'd really like you guys to just share with us what you'd like to get out of this presentation. What are you looking to learn? Because, you know, we can just make sure if we see anything that's, you know, any common threads or something that's really worthwhile, that we chime it in as we go along or we address it at the end. So, and we got a lot of people on board right now. Just start, please throw in your questions, what you'd like to learn from this presentation right now. All right, and then I think I had mentioned there's also handouts in here, so please go in there, download the handouts. However, as far as the handouts go, the presentation's not going to be available right there, but if anyone's looking for the presentation, you can reach out to us directly at support@rathasos.com. That's SUPPORT at RATHEASSOC.com. And like I said, we can get you that this presentation. But right in the handouts folder there, you can find a handful of Laars presentation bits as well. All right. Oh, so I guess that's my whole intro. So let me hand this off to Dr. Lou. Dr. Lou, you there?
Yes, good morning, everyone. How you doing, Greg?
Doing great. All right, I'm going to mute myself and you go ahead and take it away.
Okay. Well, good morning, everyone. I hope everyone's having a great day. It's beautiful and sunny up here in New Hampshire. I'm happy to be going through this seminar and basically giving in talk about the topic of optimizing condensing boiler plant efficiencies, and really want to talk a little bit about different aspects of a boiler plant. And with that, let me slide it forward to the next. One moment here.
should be able to just click or use your keyboard arrows. Click maybe the right arrow.
No, it's not moving. We have
Try clicking on the screen. Maybe give it another click.
Can you advance it on your end?
I can. Let me just try and make sure you have, oops, click the wrong button here. Sorry, everyone. Let me just make sure you have keyboard and mouse control. You should have it. Can you try it again?
No, it doesn't.
You have the mouse. There you go. Try clicking.
Yeah, it's not going through, man.
All right. So, all right, I'll be your guy. So
there you go.
Let's go right to it.
Next one. Okay. So just kind of a quick overview. Really looking at this, wanted to look at three major components: system considerations, and that really what I'm looking at there is, and for a lot of you it might be somewhat repetition, but some good thermal and mechanical stuff to be discussed under system considerations. The next section talk about condensing boiler overview. Really covers the piping control aspects. You know, what is really the deep down, what's really the secrets to high turn down boilers, and also talking about boiler plant piping and how different boilers can be piped up to optimize overall efficiency. Then the third major topic is the new frontier in boiler plant efficiencies. We'll call it the smoking gun. The last few years, several manufacturers have been developing and applying O2 trim systems on commercial sized boilers. You know, they've been in use on large industrial boilers for many years, but due to scalability and cost reduction efforts and also volumes, this new exciting technology is now also available on commercial sized boilers, and it really is the key aspect of driving and ensuring peak efficiency on condensing boilers. So if you want to move on to the next one. So here's a quick overview on some of the major factors that influence condensing boilers. We're not going to talk all about everything, but of course government regulations is one of the key drivers. Just as a sidebar, as Greg indicated in the introduction, years ago I worked for a German-based company for about 15 years, and within Germany itself, government regulations are very strict in terms of overall building design. And you know, 30, 40 years ago, they were doing all high temperature systems, 180 out, 170 return. Then towards the late 80s, they started really honing in on increasing overall efficiencies, lowering maximum supply temp, going out to the building for space heating, bringing back the return temp, and then with the advent of condensing boilers in the early 90s, for new construction, they came up with a new standard, basically dictating that for new applications, the maximum supply temperature could not exceed 122 degrees, and the maximum return temperature on coldest day could not be above 110 or 105 degrees, and they call that, translated, the new heat. And it really drove, first of all, you get, of course, get optimum performance on your condensing appliances. It drove a major driver towards the expansion of radiant floor heating, as well as larger radiators and larger thermal surfaces to effectively heat the building. What we're going to focus on in the next few slides, if you want to go on to the next one, Greg, is what we want to focus on here first is the system-related aspects and really how these system-related aspects drive efficiency and how we can look at the system to ensure peak condensing operation. Two key items here are return water temperature and as well as the overall heating system design. Moving on to the next slide. I'm sure most of you have seen this slide before in some shape or form, where we're looking at return water temperature as a function of boiler efficiency, as a function of return water temperature, and there's the magic number about 130 degrees, which reflect the dew point of natural gases. And the dew point of natural gases meaning the temperature of the flue gases, or the heating surfaces that the flue gases need to transfer heat energy to, so that we can actually recapture some of the water vapor that's being liberated as we burn natural gas. Return temperature to the boiler above 130, 140, no boiler will condense. It's simply physically not possible. Return temperature at 130 or less, we now definitely can have a boiler start condensing, flue gases condensing on the flue side of within the boiler, and us then reclaiming some of the thermal energy that would normally go up the chimney. So this 130 is a critical number to keep in mind. Moving on to the next slide is a very simple system. You know, whether it's a residential or commercial system, you basically have your expansion tank. If you pumping the heat from the boiler out to the system. In this case, the image shows good old cast iron radiation, very comfortable way of heating. And again, in order to get the condensing, we need to bring it down to 130, 135 in order to even get a chance to condense. However, there's some other factors, we'll get into those, that are also need to be correct. Otherwise, that point of condensation will be 125, 120, or even less. But really, the 130, 135 is the very first requirement. Looking at different types of systems, you know, whether a new application or a retrofit application, you know, there's different types of heating emitters. We can have baseboard, fan coils, you know, some domestic hot water production. You know, those are typically considered high temperature loads, where on design day, we're typically looking 180, 190 that needs to hit that radiation in order to get a substantial amount of heat out of it. There's other types of radiation, cast iron radiators, oversized baseboard, or low mass radiant floor heating, where you may supply that on your mildest day, maybe with 100 degrees, on design day around 140, in order to get the required heat into the space. And then we have some low temperature systems, such as radiant floor heating, concrete floor heating, or outdoor snow melting, where one will typically run water temperatures ranging between 80 to 120. 80 again on milder days, 120 on design days. Tying that all into a system, I mean, this is very high level, but you know, the concept of outdoor reset has been in the market for many years. Well, you look at outdoor temperature and regulate your water temperature going out to the system, and even the water temp in the boiler based on outside temperature conditions. Milder days, we don't need as much heat, so we basically spoon feed the heat to the radiation, whether it be baseboard or in floor, wherever it might be. And then on the colder days, we ramp up that water temperature. With new condensing boilers, you know, outdoor reset's been around for many years. With traditional boilers, the way those are typically operated at 140 and up to ensure that we're not condensing in the boiler. And then the outdoor reset was typically done through a 3-way or 4-way valve out in the system. You know, with new modern condensing boilers, we can do the outdoor reset directly through the boiler, pick up that additional efficiency gain, ensure that we're actually resulting in condensation. And what we see here is we see the outdoor reset curve, which is the supply temperature coming out of the boiler. Likewise, we would have a return temperature curve underneath it, and that would really then dictate at what point outdoor temperature we would see this condensation occurring. Moving on to the next slide, this is your typical high temperature curve. You know, you may have an existing apartment building, new boilers need to be put in. All we're looking to do is take the old boilers out and put high efficiency boilers in. We still need to supply 180, 190 on design day to the system, and at about a 160 return. And you know, this is based on, say, design conditions being 10 to 5 degrees Fahrenheit. That return temperature will be below 130, 135, down to about 25 degrees Fahrenheit. Meaning that anytime we have heating above 125 degrees outdoor temperature, we will be condensing. Only when we're in the middle of winter and we really need to bring that high temperature heat out into the system, will our return temp be above 130, 140, and we will not be condensing. So even a high temperature system, if there's no way to drop that return temperature down, you know, one can get a decent range in condensation operation. You know, bulk of the heating season is well above, typically above 25 degrees, so only on cold days we wouldn't be in condensing operation. If we now move on to a medium temperature system, or again, this could potentially be, okay, here we see, no, let's go to the next one slide. The previous one, Greg, back up. Yeah, here we go. Yeah, so if we look at this high temperature system, based on Boston, where design day is 7 degrees, and here's the weather bin data plotted for Boston. We see here that down to about 28 degrees, we will actually be in condensing mode, and we would not be in condensing mode for about, say, 25% of the time. So even on a high temp system, 75% of the heating season would be in condensing mode with a high temp system. Moving on to the next slide, we see when we have a medium temperature system, so where here we may have our supply temperatures ranging up to about 160 with a 65 with a design return temp of 140. This could be, again, could be the same apartment building, but now maybe the building has over time has been upgraded with higher quality windows, maybe more insulation was added, into the attic or into the walls. So the overall building envelope is much better insulated, and we most likely might be able to heat that building out much lower temperatures. And we see, if we then move on to the next slide, we see that now with this lower supply and return temp, we achieve condensing operation down to about 14 degrees outdoor temperature, and we're only 3% of the heating season. Only about 135 hours in this case would the system operate in a non-condensing mode. So just by not just looking at the baseboard or the radiation in the building, but also by having efficiency upgrades on the building envelope, we can, in existing applications, drive down our supply temperature and the resulting return temperature to reap the benefit of condensing appliances, of condensing boilers over the bulk of the heating season. So moving on to the next slide, we can see here, insulation as always, it's something as simple as insulation, but also another factor that can really help us to ensure more condensing operation is to see if we can increase our water temperature drop, our delta T in the system. Especially in retrofit applications, the old systems were typically designed around a 20 degree delta T. For some reason, it really made the math easy. Pump sizing, everything just comes out very nicely. But especially if the building has seen thermal upgrades, going to a 30 degree delta T will most likely very easily keep that building very comfortable during the entire heating season, or maybe even a 35 or 40 degree delta T. And what that does, of course, is yes, we still can supply the 180 out to the system on design day, but now our return temp drops that much more quicker, could be dropping down to 140, 150, and we will shift and dramatically increase the number of hours that this system will run in condensing mode. In addition, by running these larger delta Ts, if there's any upgrades in the piping system required, or it's a new installation, we can, lower flow rates translate into smaller pumps, smaller pipe sizes, so a lot less equipment to be installed, lower operating costs from an electrical standpoint, and overall lower capital costs. And then, the added benefit, of course, by having a much greater window of condensing operation on the equipment. So increasing your delta T in the system has been, a frequently used strategy in new buildings as well as in retrofit buildings to take what used to be a high temperature system and turn it into a lower temperature outdoor reset driven high efficiency system. One thing that sometimes, especially when new applications, moving on to the next slide, new applications, especially when we use terminal units or any type of terminal units in new applications, if we're dropping our water temperature and using fan coils, of course, we need to realize that since we're feeding the fan coil with a lower temperature water or baseboard, for instance, we may need to increase the size of that radiative surface area. just as I started off a moment ago in terms of relating what, how the industry changed, the building industry changed in Germany, when they made and have implemented these different efficiency upgrade programs. 25, 30 years ago in Germany, most residential boilers were sized based on the heating load of the building and the heating load of the building envelope. Now, many of these residential boilers in Germany, typically the boilers also used for domestic hot water production, because the dramatic increase in improvement in building envelope insulation, the boiler sizing is now typically dictated on the domestic water load and no longer on the heating load. However, on commercial applications, when you do want to size for high efficiency, lower temperature operation, you do have to make sure that you size your terminal units appropriately. Moving on to the next slide, here we see just a kind of some overall conclusions from a system standpoint. First of all, outdoor reset is a perfect way in ensuring excellent condensing operation over a major portion of the heating season. Only maybe during the very coldest days of the year, we may not run in condensing operation. Of course, the key critical aspect here is driving that return temperature down as low as possible. Using a larger delta T is a perfect way in accomplishing that. And then by doing so, we can also reap the benefits of smaller piping, smaller pumps, reduced electrical cost, and overall driving boiler plant efficiencies up. Moving on next, I want to talk a little bit more about the details in terms of piping layouts and how we can use piping layout in high turndown, and some of the key things that we need to be watching out for in terms of water tube and fire tube, and how the different boiler technologies play into these piping arrangements. In the last 5 to 10 years, I think the industry overall has really shifted from a 3-to-1 or 5-to-1 firing rate or turn down to a 15 or 20-to-1 turn down. This has been driven by the introduction of premix burners. Premix burners where the air and fuel ratio are very carefully monitored and adjusted over the entire firing range, as opposed to large forced draft burners. And we'll talk a little bit about the combustion side of those things in a little bit. But basically, 5-to-1, the boiler runs from 200,000 up to 1 million BTUs. 20-to-1 now, you have that boiler running from theoretically 50,000 BTUs up to 1 million. So what that really allows us to do is really fine tune and align the boiler heat output with the heat loss in the system, and really eliminate or drastically reduce the cycling on the equipment, and really puts the entire heating system and the heating plant, the boiler plant, almost in a cruise control mode. Looking at outdoor temperature, looking at system supply temperature, and then the plant itself very carefully delivering just the right amount of BTUs that the system's asking for. And as demand increases, the firing rate increases, and if necessary, additional boilers increase to satisfy the load. Moving on to the next slide. The key point of this slide is really a couple of things. First of all, we see that the efficiency plotted on the left-hand side versus water temperature versus return water temperature. As the return water temperature drops below 130, 135, we see that this efficiency starts to increase quite dramatically. But even at any given return temperature below 130, we see that we pick up anywhere between 1 to over 2% efficiency gain as we go from the blue, which represents the 100% full fire input, to the yellow line, which represents the 5% high turndown input. So yes, we can run a boiler at 80%, or we can run 2 boilers at 40%. And that will you'll really easily pick up an inch and 1.5% efficiency gain by doing that. Plus you have the redundancy and the overall improvement in reliability. So really, by having this high turn down, we increase the overall efficiency. And then we need to look at boiler technology, moving on to the next slide, in how can we best use that. Talk a little bit about control here. Prior to the onset of high turn down boilers, most boilers would be operating what I would call in a sequential cascade mode. Could be either high mass or low mass boiler, but they would typically be low turn down, where boiler would operate, say, between 30–40% up to, say, 100%, and serial cascading would take place. Once the first unit ran up to 80%, it would basically bring on number 2, and now the 2 of them would run together, and then eventually number 3 would kick on, and so on. In these types of scenarios, we really rely on each individual boiler by itself. Typically, these would be piped up with primary, secondary piping with individual boilers, individual pumps in each boiler, and then the main building loop could be running in a variable primary mode. There'd be some lead lag rotation, maybe some equal runtime on boilers, and so you would have, yes, you would have the redundancy, but you would have a fair amount of piping. Boilers that require a specific flow rate or are quite flow rate dependent, no, it's a perfect way of piping up these boilers. And moving on to the next slide, we see what that would look like in a typical application. Now the blue line here represents the return water coming back from the system, and then we have a main system pump, a variable speed pump pumping the building, school, large apartment building, whatever it might be. And then from the main header, we have 2 closely spaced T's with a common reverse return piping with individual boiler pumps, where each pump basically pumps through its boiler as that boiler is engaged through the control system. And then as the thermal load, as the building load increases, the control system will bring on number 2 or number 3 and bring on those individual boiler pumps. So for those boilers, water tube boilers, which typically require a specific flow rate, or it's a perfectly fine way, we're ensuring that each boiler receives that cold water temp. We're not doing any blending on the return temperature. We're just bringing that cold water directly back into the boilers and theoretically the high delta T through the boiler and achieve the efficiency that we're looking for. Put some of the more recently boilers that have been on the market, moving on to the next slide, especially when we have high turn down. Now we can, instead of relying on boiler number 1 for a substantial portion of handling the heating load, now we can bring on the second and a third one much faster. So it is with, instead of sequential, I would call this more of a parallel cascading operation. Very suitable for low mass, high turn down boilers. And now instead of having an individual boiler pump on each boiler, we can now use what is called variable primary piping. And now we use individual isolation valves on each boiler to ensure that we're only flowing water through a boiler. And here we see the overall piping diagram. We have our variable speed pump pumping the system, and then we have the same bank of boilers, but now we don't have the individual boiler pump, but now we have individual 2-way control valves on the supply side of each boiler. During low demand conditions, low flow conditions, we may have 1 boiler operating, but as we now have high turn down boilers, and we can easily maintain the load with 2 boilers running at 15–20%. We now, in that case, we operate through 2 boilers, and as we go into the colder days of the year, or the system comes out of night setback and certain zones kick on, the variable speed pump will ramp up its velocity, and depending on the control system, the boilers will bring on number 3 and number 4 as needed. But overall, really trying to achieve and maintain the heating load by operating the boilers at as low as a firing rate as possible. Moving on to the next slide, I think we got a little quick design example here. Say we got we're going to design a primary only variable flow hydronic systems. We have a 3.6 million BTU design load, a 400,000 minimum load. say we want to reset between 100 to 180. So we're still looking at a typical maybe retrofit apartment building. We want to bring the delta T up to 30 degrees. And we're looking to have, N+1 redundancy. So 2 boilers should be able to handle load. So we basically have 2 million B2 boilers with variable speed primary piping. And moving on to the next slide. Some of the things that we want to consider here is, we want to make sure, typically you're always going to have some flow available. You always want to have some flow through the system. In some cases, it might be just a pressure activated bypass. And the key aspect here in optimum plant design is really to make sure that the heat that's being generated by the boiler plant is basically consumed at the same rate in the building. So any changes in the building, loads coming on or zones shutting off, the boiler plant will simply respond by having the burners ramp up and down and not necessarily have the individual boilers fire. Using high turndown boilers gives us a lot of flexibility. Some math here, we can read that. I'm not going to go through those, but moving on to the next slide. Just real quick, we have a maximum load of 3.6 million BTUs. We've got a design temp of a design delta T of 30. That basically leads us to a maximum flow rate of about 240 gallons a minute on design day. A minimum load of 400,000 BTUs, which gives us about a 37 gallon a minute flow rate. So our variable pump should be running between 30 and 240 gallons per minute. And if we then move on to the next slide, we can see here the 3 boiler units with a variable speed pump. We have a number of zones. There's at the far end, we see a pressure activated bypass. So if all the zones are maybe closed, then we simply have the variable speed pump drop into minimum speed and pumping that water through that pressure activated bypass. As additional zones open up, the variable speed pump will ramp up because it sees less of a pressure drop. We're looking at outdoor temp. We maintain our certain supply temp at 100 degrees, and then with 30 degree drop, we see about a 20 to 30 degree temperature drop on the boiler side. So during the heating season, on mild days, we'll have 80, 90 degree boiler temperature coming back to the plant, only 1 boiler in operation. As now zones kick in, moving on to the next slide, we see now we're running at design conditions, all zones are open, and we can have all 3 boilers, all 3 valves open, and even then we're satisfying the entire load with boilers operating only at 60%. If we were to have some type of issue with one of the boilers, we still have the overall redundancy, and the 2 boilers would easily be able to handle the load with the 2 boilers even running at less than 100%. So this is a variable primary single pump system. You may have a duplex pump for redundancy, but then especially with fire tube design boilers, which have a greater degree of flexibility in terms of flow rate through the boilers, we can install high efficiency systems with very simple piping, really limiting the electrical consumption as much as possible, and have a highly efficient system, in this case running a 30 degree delta T on design day and achieving condensing operation through the bulk of the heating season. Moving on, one key aspect that I briefly mentioned, I just want to focus on just briefly here is the use of these motorized valves. Couple of things, first of all, these motorized valves ensure that we're only sending water through a boiler that's actually active part of the system. So we're not going to have a boiler become a large radiator in a mechanical room and just sitting there and giving off heat without being active part of the system. Of course, we always want to make sure there's at least one of these open, otherwise the main system pump would be deadheading. And the overall operation of the motorized valve is typically programmable, where you can have it remain open for a certain amount of time, or you have an auto close after the burner shuts off. And so their functioning is fully programmable. If on larger systems, you can set it up where you have maybe you always want to have at least maybe 2 boilers on, so you can have a min on or min open of 2, and then have the system bring on additional boilers as necessary. So what they really do also is ensure that we're maintaining, especially under low flow conditions, we only have flow through 1 or 2 boilers, so we're preventing nuisance high limit trips. We're not pumping water through all boilers, we're just pumping it through 1 or 2. And always want to leave the lead boiler open, the lead valve open, so that we're not deadheading the pump. And it's the valve operation itself is typically directly linked to burner operation with a certain programmable time where you leave the valve open until after maybe 20 minutes or half an hour until after the burner shuts down. Keep in mind that with high turndown boilers, these boilers will typically run virtually continuous. You know, you may have automatic rotation, so that on a weekly basis or daily basis or weekly basis, you may designate another boiler to become the lead. But once the system's up and running, with the high turndown, you know, the boiler will hardly ever shut down unless we get into summer mode conditions. Moving on to the next slide, I want to talk a little bit more about the chemistry side of things, and this really gets into combustion and also how we can really ensure that a condensing boiler operates at its peak efficiency. Moving on, looking at this slide here, it's a lot of stuff here. I'm not going to go into detail, but what we're really seeing here is the chemistry of the combustion of natural gas, CH4 in the upper left-hand corner, combining with air, combination of oxygen and nitrogen, and then of course producing CO2 and water vapor, and then a lot of nitrogen and some nitrogen and nitrogen oxides. Again, a lot of nitrogen simply just goes along through the combustion zone, and in the lower right-hand corner we see the overall chemical reaction. The key part here is the water vapor up in the upper right-hand corner. In a condensing boiler, what you want to do is you want to recapture as much as possible of that water vapor. We'll dig into that in a moment. Moving on to the next slide, there's a couple of challenges in terms of natural gas combustion. First of all, you know, we use combustion air. Air is about 78 to 80% nitrogen, about 21% oxygen. We need some excess air in order to make sure that we burn all the carbon to CO2. If we really limit our excess air, then we can very rapidly result in incomplete combustion and CO2 levels rising very quickly. Another critical aspect is, you know, there's a lot of nitrogen that's come along through the combustion zone, and NOx levels, whether it's N2O or NO2, there's different versions of NOx, they tend to increase very rapidly with flame temperature. So we want to keep the flame temperature relatively low, otherwise our NOx levels can go very high. Another challenging factor is if we have a lot of excess air. So you may think, okay, we need excess air. You know, put in some excess air. We'll keep our flame temperatures low. Our NOx levels will be low. We need some excess air to reduce CO, so that's good. Well, if we put in a lot of excess air, what we're really doing at that point in time, if you think about a hot, muggy day in the summertime, and you're adding just air to that air, just clean air, not moist air, dry air, what we're doing, we're drying out the air. And what we're doing when we have a condensing boiler and we have the flue gases, CO2 and water vapor going up the chimney, what we really want to do with a condensing boiler is have that water vapor go back to liquid water and take that heat and convert that heat back into usable heat by putting it into the boiler side. So excess air is really an enemy in terms of condensing operation. And we'll get into some of those details a little bit more. Lastly, but not least, also very important is we want to, of course, have reliable operations, low emissions, because, you know, people just want to put the plant in, turn the unit on, make sure it's set up properly, and then have it operate under a wide range of operating conditions. So these are all challenges, and that from an engineering standpoint, that's what our team tackles with and addresses. And with new technology, a lot of these we can address all these challenges here. Moving on to the next slide. Here we see a little bit, I talked a little bit about the excess air. Here we see the overall combustion of methane again. And what I've plotted here is, if we look at it on a molecule basis or a molar basis, it shows the effect of having some excess air. So the very top line in the table represents no excess air. We have just the right amount of air. We're having no O2 at the end. We got O2 going in at 20%. We burn all the O2, so there's no O2 in the end, and we end up with about 12% CO2. That's stoichiometric combustion. All the air that's available is consumed, all the methane is consumed. We got CO2, we got high water vapor going up the chimney. Of course, that's the fantasy world. We need to have some excess air. And what we see in the red box is the typical range of excess air that are being used in boiler combustion. You want to keep that excess air as low as possible. If you have 26% excess air, that means your O2 at the end will be about 5%. Your CO2 is going to be 9.5. In the middle, under stoichiometric, I have this number called 287, which is basically the total volume and mass of combustion products, of chemical reactants going in, and chemical products coming out of the burner. And then the circle section represents the effect of excess air. So you can very clearly see that as the excess air percentage goes up, there's a lot more material that goes, there's a lot more excess air, a lot more nitrogen that goes into the flame zone, reducing our flame temperature, but at the same time also diluting the moisture level of the hydrogen, of the water vapor going up the chimney. And you can really see how that really becomes a drag on our CO2, and shortly we'll talk about how that actually affects our overall efficiency on a boiler. Moving on to the next slide. Thank you. Here's very simple depiction where we want to have the water vapor cool down inside the boiler, occurring at about 130 degrees, depending on our O2 levels, and turn it into liquid, and then basically putting that heat back into the boiler. A couple of things that will occur when moving on to the next slide. A couple of things that will occur with flue gas condensation. First of all, of course, we regain a portion of that latent heat from the condensate. We're not having all that water vapor go up the chimney. We have lower flue gas temperature, so we'll also have an increase in the sensible heat gain. And also, the boiler will not be nearly as hot. And our venting system, which is, a good portion of the venting system is inside the building typically, will have a lot less heat going up that venting system. So we're really keeping the heat where we want it. Moving on to the next slide here, we see really what the effect of CO2 is on our dew point. So looking at the graph here, at 10% CO2, our dew point of the water vapor in the flue gas is about 131 degrees. That means at 131, that's when that water vapor will start to condense into and turn into condensate. If we have our CO2 running at 7%, or 8% rather, now our dew point actually drops to 122 degrees. So proper setup on the boiler and maintaining high CO2 levels and relatively low O2 levels will really ensure that we have proper what is called dew point control and really achieving the efficiency that the manufacturer is listing on the equipment. So we want to make sure we keep our CO2s high, keep our O2s low, keep our dew points high, because that's really when the water vapor starts to condense and we'll have the condensate coming out of the condensate drain. Moving on to the next slide, we see here is a slightly different form here, but we see again how that the change in the CO2 from say 9 to 10% down to 6 or 7%, how that will change our dew point by 10, 15 to maybe close to 20 degrees. So it's a very critical aspect to really ensure we control and minimize the amount of excess air. And this is then moving on to the next slide. And the control of the excess air is really, I would call that the smoking gun in terms of ensuring that that boiler will really achieve the efficiency that is listed on the literature and that the manufacturer claims on the on the product. So really to make sure that high efficiency equipment, high turndown equipment operates efficiently over its entire firing range, one really needs to look at the fine print and what the manufacturer's recommendations are in terms of combustion settings, both at high fire setting as well as low fire setting. And I would almost think it's even more critical to look at the low fire setting versus the high fire setting, because in most cases you're going to have high turn down, you're going to have multiple boilers operating, you're going to have boilers operating at 10, 15, 20, 25%. Yes, you want it to, it may run once in a great while at 100%, but the bulk of the heating in the operation will be done at that low firing range. So really see, you know, here we got one manufacturer running at high fire 9, low fire between 8 to 9.2. We have another manufacturer that lists their CO2 levels at the 2 to 4% range under low fire conditions. So here we see, yes, the product may run efficient at full fire condition, but at low fire conditions, we're having very low CO or very low COs, a lot of excess air, and we're going to have a very poor, a very low dew point. Moving on to the next slide. Talk a little bit about O2 trim. You know, what is O2 trim? O2 trim is a system where we're looking at the O2 levels or CO2 levels, or really the O2 levels in the exhaust, and really saying, okay, we really want to make sure that this O2 level does not exceed a certain level, and use that as a feedback system into the combustion. It's independent and typically results into independent control of fuel and air delivery. Usually, almost everyone is using a variable speed blower, and basically the O2 trim will make a fine adjustment on that blower speed to ensure that we're not having excess O2 trim, to really limit that O2 trim. And it requires typically a premix burner, so we get good mixing between fuel and air. And some systems run continuous, some systems run intermittent, and in most of these systems also will typically periodically calibrate that O2 trim system, making sure just let it run when the burner's off, and it should be listed, basically sensing the 21% O2 value in common in regular air, and they use it as a fine-tuned calibration point. Moving on to the next slide here. Here we see a control system, with a gas solenoid and a fuel damper. Keep clicking here, Greg. Where we have independent fuel and air control, and then moving on to the next slide, then the gas is coming in, it goes through the fuel control valve, we have an air damper, and then the air and fuel are mixed in the air fuel mixer on the intake side of the blower. The blower's pulling it in, microscopically blending and mixing the air fuel mixture together, sending it into the burner, into the boiler for burning. And then with the O2 sensor in place, moving on to the next slide, we're basically sensing fuel and air, sensing fuel and air, and along the entire heating curve, along the entire calibration curve, we have 9 points where at the factory level, the fuel valve and the air damper are adjusted and fine-tuned, and then anywhere between those 2 points, they may automatically adjust themselves in harmony. And then the O2 sensor will pick up the O2 levels either in the exhaust or in the combustion chamber, and then make fine-tuned adjustments, make fine-tuned blower speed adjustments to effectively trim and keep that O2 level at within the desired range. Moving on to the next slide.
Hey, Lou, just want to give you about a 10-minute warning. All right, so just want to start wrapping up in the next 5-10 minutes so we can get to the Q&A portion.
Yeah, sure. Yeah, move on. You got to click this one a few more times. Yeah, most of the car manufacturers using an automotive O2 sensor. Again, just after initial warm up, it kicks in. A lot of manufacturers look at a 9 or 10 point curve where these are preset at the factory, and the system interpolates between these points. Moving on to the next slide. Yeah, you can click through these fairly quick here. So we have an overall control system, looking at the gas, looking at the air, setting those positions based on firing rate, and then making the O2 sensor in the control system, making it fine-tuned speed adjustment. Moving on to the next one. Another manufacturer, very similar setup. You know, here the O2 sensors in the combustion chamber, and sends a signal back to the boiler controller, and the boiler controller again makes a speed adjustment on the blower. And moving on to the next slide, here we see the hardware, the air fuel valve, which basically regulates or sets the relationship between fuel and air, and then the blower making a fine-tuned speed adjustments for trim functionality. I like this graph because I kind of want to spend a few moments and illustrate what's going on here. This was a boiler in operation during our development period, and the red line is representing CO2 levels at about 140-degree water temp without the trim, and we just operated there for a while, ran at different firing rates, and then we turned on the trim function and let the unit adjust and adjust the blower speed to bring the O2 levels or the CO2 levels up to the desired point. And what we see here at say a trim function 5, we see our CO2 going from 7.5, a little over 7.5 to 8.8, 8.7, 8.8%. So we see almost a 1 full percentage point increase in the CO2 level just by having that trim function on. Okay, so think about this. This boiler was installed last year, 2 years ago, without the trim function. It would be running around that red curve. With the trim function on, the system will automatically ensure that it's running at the desired levels and ensuring higher CO2 levels and therefore higher O2 levels. So having the trim function built, trim function enabled, gives us this automatic boost in efficiency and increase in performance, because here, we're running with the trim function on, we're running in combustion-wise speaking at optimized settings, and that's what the O2 trim function ensures. Moving on to the next slide here. Just real quick on the Laars trim, like there's different O2 trim systems. One of the features on our trim system is that we have continuous trimming or continuous O2 monitoring and trimming if necessary within 2 minutes after startup. There's other systems out there that do periodic trimming. Our O2 trim system is available on both fire tube boilers, for space heating applications, as well as water tube boilers, which can be used for both space heating as well as potable water, volume water applications. Some of the additional benefits of O2 trim is that, if certain things happen on the outside of the system, there's some automatic outdoor temperature compensation, because if the outdoor temperature drops, the air will become more dense. The O2 trim system will pick up the increase in O2 and will then make the necessary adjustment. Likewise, if you have a mechanical room with automatic combustion air dampers to the outside, if say one of these dampers kind of gets stuck and maybe somewhat inhibiting the flow of combustion air into the mechanical room, the O2 trim sensor can make some adjustments for it. I mean, if there's no air available, the O2 trim system cannot fully compensate for that, but if there's some misadjustment in the system, it can most certainly accommodate that. The system that Laars is using is the LMV system from Siemens with a preset 9 calibration points. It's been formerly used and has been used on much larger combustion systems as well. So it's been on the market for many years. And it also provides advanced diagnostics. So if this trim system is continually hitting the far end of its trim, it will send out a signal so that, hey, there might be something going on in the system and needs adjustment, but the system's still operating, whereas without the O2 trim, it might have caused a shutdown. moving on to the last slide here. I know we covered a lot of different aspects here in terms of ensuring high efficiency operation. First and foremost, it starts with a proper system design. What are the required temperatures? How can we drive these temperature requirements down to make sure that we reach that 130 or ideally 120 or 110 coming back to the boiler? Then looking at, okay, what are the boilers capable of doing and what are the system requirements? How can we really ensure that how do we pipe these boilers up? What's the capability? Are we looking to use high turndown boilers? Can we use them, set them up in a variable primary so that we can really have very fine-tuned heat output control and have it be in harmony with the heat loss in the building? Deploy an N+1 equipment selection criteria for redundancy. And then on top of that, overlay that with a O2 trim capability for optimized dew point control, improved overall reliability, and advanced diagnostics. So those are the things I just kind of want to share with everyone. I thank everyone for your time and attention, and we'll open it up for some questions and Q&A.
All right, thank you guys. Thank you, Dr. Liu. That was really great. And as promised, it was a much deeper discussion from the previous presentation. So again, thank you. That was awesome. We're going to get to the Q&A in just a minute. And again, a reminder that this presentation has been worth 1 PDH credit. We'll get you your certificates as soon as we possibly can. So the real exciting thing is for any of your people who missed this presentation, or if you would like to catch up on it again, something you missed, something you want to just kind of think about, all of our presentations, whether it be this PDH that we're doing right now, with the PDH we did about a month ago, or our 20-minute webinar series that many of you have been taking a part of, we've been uploading all of that content to our YouTube channel. So we're really building up a very nice library. So on there, you're going to find all these presentations we've been doing. But additionally, many of you are familiar with our Ken Resnick. He's our resident trainer, and we're building up a library again of technical tips. We're trying to keep things short, 2 minutes, 5 minutes, probably 10 minutes at absolute most, and just tips on our various pieces of equipment, but also fundamentals, general things. So you can find a lot of great content here. We post a lot of stuff on LinkedIn and Instagram, so be sure to friend us there as well. Also, another great resource before we jump to the Q&A, and while I'm chatting, please feel free to throw some questions in. I see a lot of people throwing questions in. Whatever's on your mind, throw them in there, and like I said, we're going to try and get to everything that's on there, but throw the questions at us. So Laars offers a really great sizing tool. It's called the Laars Right Spec. You can find it right on their website. You got www.laarsrightspec.com. That's LAARSRIGHTSPEC.com, or you can find the website simply just by going to their website. Within here, you could just tell them exactly the application you have. It's car wash, apartments, dormitory, laundry, prison. So you can plug in all these things. You click on any one of these, and then you can fine tune the details. It'll give you a nice printout, give you options of various equipment selections. You could determine, do I want to have storage or no storage? Do I want to have 4 storage tanks, 1 storage tank? A variety of different things. It's very customizable. It gives you a very nice printout. If you're an engineer, this is an absolutely great tool. And then, of course, if you're a design build contractor, again, a very nice tool. So please feel free to play with it, or reach out to us, Rath Associates, and we'll help you size up anything that you need. And to that point, we are not just Laars. So for anyone who's not that familiar with us, Rath Associates is a manufacturer's rep that's been in the business now for, I think this is our 51st year. We've been representing a ton of lines, everything you need for your mechanical or plumbing mechanical rooms. We have boilers, water heaters, storage tanks, expansion tanks. I'm going to list off a bunch of things real quick, so bear with me. Circulators, heat exchangers, indirects, air, dirt, hydraulic separators, and a lot more with Calefi. We have venting from Centrotherm. We have, we have a lot of controls, thermostats, valves. We have testing equipment with TPI, glycol feeders. So I'm just trying to make you aware of everything you need in your hydronic mechanical room. we really offer in plumbing as well. So water heater, storage tanks, indirects. We even offer piping with polypropylene piping. And, you know, maybe we find that a lot of people get their first touch with us through radiant floor designs and snow melt designs. We've been doing that for decades now. So anyone has any questions, we've done many residential family, high-end residences. We do apartment buildings, you know, multi-story. We do snow melt. We've had a couple stories written in the newspaper about us as well. So we're your go-to experts on that. And the final newer kind of items are HVAC, so high-efficient ERMs to promote indoor air quality and to save energy. It's another thing with this Local Law 97 to keep in mind. So I guess at this point, we're going to open up now to the Q&A portion of this PDH session. So keep the questions flowing in. So please, everyone, write in any questions. If you have questions that we can't get to, or if you'd like to have a broader discussion, please reach out to us at support@rathassos.com. And we'll have someone from our commercial development team. So we have a whole squad here of people that can help you on any of these things. But of course, if you're more of a residential person, you know, we have a whole team, and we all can help you with that as well. And actually, before we jump to the Q&A, I do have 2 polls. Let's try this out. So let's see. I think, you know what? You have to have the screen up to be able to see it. So I'm going to just launch this only one poll. Let's see what you guys think here. So the question is, what is the return water temperature at which boilers operating at 9% CO2 will begin to condense? All right, so our options are 90 degrees Fahrenheit, 110, 130, or 150. So everyone, please put in your results, and I'd like to see what everyone thinks, what everyone gets out of this. You know, I apologize because, you know, what I would have liked to have done was have the little chart up so you could see it, but it's basically your most common chart that you've seen in the ASHRAE handbook and ASHRAE manual. So I'll just leave this up for about another 10-15 seconds, get people's thoughts, because I don't want to drag this out for too long. All right, so keep the votes coming in. All right, and I'm just going to close it out now. Again, I just don't want to drag it out for too long, get to some more Q&A. All right, so the answer was 130 Fahrenheit, and about 70% of y'all had actually gotten that, so very good. I'm not going to do any of the other polls, so we'll jump right to the Q&A. And Dr. Lou, I actually got one here for you. So you actually, much earlier, there's a question I actually have been kind of wondering. Earlier, you showed the isolation valves for the boilers when you're operating multiple boilers in a variable primary application. Mm-hmm. Would it be a better application to keep one of those valves open all the time, right, to maintain flow, to not deadhead the pump, or to have maybe some kind of bypass valve or some kind of 3-way bypass valve? This way, if you don't require any heat input, then you could actually bypass.
Yeah, you could do either or. You could do either or. I mean, both approaches would be fine. It's just that if you were to send the water back through the boiler, I mean, if you have a bypass, so basically what you would be doing then is you would be limiting your supply temperature, because you would have water flowing through a boiler if the boiler is operating, and you would also have, you're blending that water down with the amount of water that would be going through that bypass. But either one is fine.
All right, great. And actually, I'm going to introduce Bruce. Bruce, there he is. All right, so if you have any questions, Bruce, he's going to help us moderate these.
Lou, thank you. I appreciate the great presentation. Just a couple of quick point questions for you. What's the correct way to treat condensate from a condensing boiler?
Okay, that's a great question. We get asked that many times. You know, several companies have what they call neutralizing systems available. Just a plastic box with limestone in it, some chemicals in it that will really reduce or raise the pH, you know, and then make the condensate, treat the condensate so it can be disposed in, you know, through a regular plumbing system. depending on the heat exchange, the material condensate can range in pH from, I think, about 3.5 to 4.5 to 5%, or 5 pH of 5. So it normally can be quite acidic. By treating it, you're going to bring it more to the 6 to 7 pH of 6 or 7. Keep in mind that if you have a well-designed system, you can have approximately 10 gallons of condensate produced per million BTUs burned. So if you have a 2 million BTU boiler, or say in that example where we had a total of 6 million BTU boiler capacity, of course the heat load was about, I think, 3.6 or 4 million. On design day, if it was a low temperature application system or a very well designed system, we could get 30 to 40 gallons of condensate an hour. So it can be quite substantial. So definitely needs to, especially on larger systems, you definitely want to make sure you have adequate drainage available to drain all that condensate.
Keeping in mind also that's something that you want to take a look at on your routine services as well, just to make sure that your condensate is still being neutralized before it leaves for the exit system.
Correct. Yep.
Thank you, Mr. Liu. I got another question, basically a longevity question here, related to how long the life expectancy of a condensing boiler will be.
Good question. I mean, they've had condensing boilers in Europe. Actually, the first condensing boilers were developed in the early 80s on the residential side, and then towards the mid 80s, they basically started building them on the condensing side. Europe at this point in time is at least 75% condensing. The UK required condensing boilers by state law, or in the mid 2000s. Condensing boiler in terms of lifespan, condensing boilers can easily last 20 to 30 years. The material designed for condensing operation, it's the combustion systems are typically a little bit more intricate than on your either atmospheric boilers or forced draft boilers, where you have a 2-to-1 or 3-to-1, maybe a 4-to-1 turn down. But they make sure the boiler receives its annual maintenance. Get the igniters and some of those things, the flame rods, they need to be replaced on a yearly or every other year basis. Check your condensate, make sure the venting is still properly supported. But other than that, I mean, there's no reason a condensing boiler can't last 20 to 30 years.
Terrific, thank you. Lou, I just got another question that came on addressing that concern with condensate. Gentleman asked if the concern would be temperature. So he was saying that a larger sequestering volume before discharge would be helpful. Agreed?
Well, you need to have your neutralization system adequately sized for your boiler plant. The temperature of the condensate will be about 120, 130. Of course, once it's outside the boiler, it's going to start giving off heat in the mechanical room, and it's going to be lukewarm water by the time it goes down the drain.
Okay, great. And then same thing, follow up for the longevity question. Is there any different material options that are available for a longer life? I think that, you'll give a pretty simple answer as far as that goes, but the materials used are generally for the longest longevity possible, correct?
Yeah, that's correct. I mean, that's keep in mind the construction of the boiler, of the heat exchanger is the material is a critical component, but also the overall construction application. Water tube boilers are typically can be used in both the space heating as well as domestic application, because the water tube, you really control and confine where the water flows, whereas in the fire tube design, those are typically more suitable just for space heating application only, because in a hydronic application, you're basically reheating the same water and you're not introducing new oxygen all the time. So water tube can both be space heating as well as volume water heating. Fire tube typically only in space heating applications. Materials, they're typically your 316, 439 stainless steel materials are the materials of choice.
Hey, Lou, it's Greg. I just wanted to kind of piggyback off that question. So I've also seen aluminum as well. So maybe just a little bit of a deeper explanation of the benefits of the 439 and other stainless steels versus aluminum.
Yeah, no, it's a very good question. You know, having been in the industry for 25 years now, and also worked at a couple of different manufacturers, you learn a little, see different things, you learn a lot of things. And one thing I've learned about with respect to aluminum is, aluminum in the U.S. has over the past 10 years has developed somewhat of a negative connotation in the market, whereas in Europe, the prevalence, the split between aluminum and stainless steel as heat exchange material of choice is about 50-50. And one of the key parameters, key drivers that kind of resulted in that kind of negative perception on aluminum is that in the U.S., and I learned this over the years, both natural gas and propane, mercaptan is added so as an odorant, so one can smell the gas when it's outside of the piping where it shouldn't be. What I've learned over time is that the U.S. Europe has stricter requirements in terms of the amount of mercaptan that's added to either the propane or the natural. And with the higher addition of the mercaptan here, typically in the U.S., that can have a negative degrading effect on the aluminum on the flue gas side. Not so much on the water, but on the flue gas side, where it will actually start corroding and removing some of the aluminum material, where stainless steel is not exposed to that flue gas side corrosion or erosion of the material. Stainless steel typically creates a hermetically sealed layer around the material, and that's why we call it stainless steel. And that protects then the material underneath. Maybe it's a little bit of a roundabout way of talking about it, but it's definitely seen some erosion of aluminum heat exchangers on the flue gas side because of that.
Great, thank you.
I'm sorry, Greg, to cut you off. Lou, just jumping in on that same topic with the aluminum. I think maybe some of the issue that we have maybe seen here in the past with it has to do with system inhibitors as well. When you're adding inhibitors to the system, the aluminum's not having a great reaction to that. Is that correct?
That's another component. Yeah, that's another component. Absolutely, absolutely. Keep in mind that especially in Germany, but in Europe in general, there's a lot more regulations, not only in terms of building design, but also heating system design. U.S. is the land of the free, and I typically really believe in that, and been here now in the U.S. for over 40 years myself. And there's different considerations, different practices, and different people do different things, and in general, I think the stainless steel is more of a robust material and is more suitable of handling different conditions, whether it's on the flue side or on the water side.
Great, thanks, Lou.
Okay.
So staying on the heat exchangers, what about we've even seen cast iron on condensing boilers. Thoughts on that?
That's a little bit of a tricky thought, I would think. I think over time, I mean, the nature of condensing is that you're going to have flue gases on the flue surfaces of a boiler. Not necessarily the entire boiler, but at least the lower portions, the lower temperature portions within the boiler. And yes, cast iron you may have fairly thick walls, but over time, it will rust. It will, over time, the condensate being very acidic will impact and have a negative impact and degrade that cast iron surface material over time. Short term, I think it's going to be fine. Long term, I think you're setting yourself up for a boiler that's not going to last as long as one would have expected.
Lou, I have possibly a system setup question here. Is the supply water temperature to a cast iron radiator lower than the supply temp to fin tube radiation?
Possibly. I mean, of course, many times cast iron radiation's been around for many years. So when this building was put up, the windows were maybe single pane windows, limited insulation in the attic. So over time, as the building envelope has received more insulation, the radiator is not going to put out any more heat if you give it the same temperature, water, but the building's not going to need nearly as much because it's much better insulated. Likewise, on baseboard, 20 degrees has been a very normal, designing systems around 20-degree delta T kind of makes the math go easy. And but baseboard can most certainly put out heat at a larger delta T. So it really got to take a look, really a holistic look at the building, especially in retrofit applications. When was the system put in? What were the current operating conditions at that point in time? You may have buildings where when the cast iron radiation put in, it was a steam system. At some point in time, the system was converted from steam to hot water. The existing boiler is probably a high temperature boiler because it's a non-condensing boiler. The system's been running kind of in an on-off mode. And, really, especially cast iron radiation, even baseboard, ideally, if you could run the system on continuous circulation with where the water temperature's in harmony and is in line with the outdoor temperature conditions, then instead of having an on-off type system, you kind of have a continuous operating system. You may have some control valves that shut down small zones, but in reality, a building's losing heat anytime the outdoor temp is below 60 degrees. So if we can supply it with the right water temperature on a 50-degree day, on a 40-degree day, on a 20-degree day, then as long as we have the right amount of heat circulating, we really achieve optimum comfort. And that's really what, cast iron radiation, the steam radiators were designed that way. They're always warm, they're hot, and especially if they're hydronically driven with a non-electric thermostatic valve, you can really have each radiator then become its own temperature zone. You have a system running on constant circulation, and you're really spoon feeding the radiation with the thermal energy that it needs to maintain comfort levels in that space.
Great. All right. Thank you for taking that.
All right, I got another, I think one more question here. If anyone has any other questions, we'll keep hanging on, so just keep firing them in. But this might be the last question. Where'd it go? Well, this is maybe a bit more of somewhat of a recap sort of thing. But I guess what would be, let's see, where is it? Where'd it go? There it is. Tips for retrofitting existing hydronic systems that want to go into a condensing application and actually achieve condensing efficiencies.
Sure. Yeah, no, that's a great question. That's an excellent question. I think the key part to answering that question was really getting a good understanding how the existing system is operating. Find out from the customer, if you can find out from the customer, property manager, somebody, if there have, during the heating season, if there's any cold spots, make sure the system is balanced. If there's any pain points that they've experienced with the existing system, especially from a system standpoint, get an understanding. Especially on a commercial application, might be a little bit more challenging, but get an understanding of what their return temperatures have been in the past. If the customer, the property manager can have an idea in terms of how much cycling they see on their zone pumps or thermostats, because all these items are really indication of, because the reason why a thermostat is cycling is we're putting in heat into that zone, and then we put too much in, and then we got to shut it off again, and then we turn it back on. So ideally, if you just put in just the right amount of heat, we can basically always put in a little bit of heat, and we have optimum comfort. So looking at those types of things, of course, the existing system, not being a non-condensing boiler, does not allow, cannot run cold water temperature back to the boiler. Looking at how old the building is, kind of look at the radiation, make sure it's fully accessible, and then see if there's ways, really verify for yourself how one can go from a 20-degree to a 30-degree delta T possibly, or maybe a 40-degree delta T, so that you can really drive down that return temperature. And depending on how elaborate the system is, and what I mean by that is, is it all baseboard radiation? Is there maybe a section of baseboard, high temp baseboard, and maybe is there a radiant section? There's certain ways where we could also return some of that piping and set up return or have the discharge of the baseboard radiation may go and feed the radiant floor heating, so that we can actually achieve a lower temperature by feeding lower temperature water into that radiant, so that we can overall lower that water temp to the boiler. A lot of different things to look at, and what may work in one application, you may need to use somewhat of a different approach in another application. And I think that's where Rath Associates and their commercial development team can be, can really be of great assist. And I'm most certainly available as well to address any application-related questions.
Great, that was a great little plug right there. Appreciate that. but you know what? It really is a great question. So I really appreciate that question that came in, because I mentioned it earlier. We all know this local law 97, or at least everyone should be aware that it's coming around the corner. So, the government is looking for essentially to minimize the carbon footprint of every building, and they're going to tax people. So there's going to be major overhaul requirements based on the mechanical system. But one thing that wasn't touched upon was that it's not just the mechanical system. I think a lot of this local law 97 is really going to affect the building envelope as well. So when it comes time to starting to redesign and reconfigure, like, okay, how do we get these people pretty much code compliant, if you want to call it that? A major look is going to have to be at the building envelope. If you can tighten that up, then of course you can now utilize lower temperatures. It kind of ends up being a big snowball effect, right? I mean, you tighten it up, you need less energy to begin with, and then on top of it, you can use lower temperatures, get the condensing with the condensing boilers, which, by the way, I believe as of the most recent New York City Energy Conservation Code, condensing boilers, believe it or not, they're going to be expected to condense. Believe maybe the Department of Buildings or whoever's kind of overseeing these things is really going to look to see that return water temperatures are within the condensing range. So just keep that in mind as well. So that's just, I guess, the final thing I really wanted to leave everyone off with. I don't see if any other, let's see, is that a New York City local law 97?
Yeah, I got one other comment with respect to in retrofit applications ensuring condensing operation, and that would be using a lot of buildings now have makeup air, and especially in the wintertime when we know the boilers will be running at higher water temperatures, so you really need to look hard for a way of getting cold water back into return side of the boiler. And one way of doing that is having outdoor air reheat, or preheating fresh air going into the building, especially in wintertime when that air is very cold. It's an excellent way. It needs to be heated anyway, and so and use that to have, first of all, better air quality, and secondly, find a way of while the boiler is running at high temp, find a way of really dropping that delta T down and getting back that cold water temperature that we're looking at.
Yeah, I'm glad you brought that up. And so again, that does segue us over to that, or not segue, but that does bring up that line that we have with the Building Performance Equipment, BPE. So like Dr. Lua just said, it'll improve your indoor air quality and save energy. So that's a very, very great point. When you're bringing in a lot of makeup air into the building, it could be as low as 20, 10, 0 degrees. It could be below 0, right? So if we can make sure that we're preheating that, utilizing an energy recovery ventilator, or energy recovery module, again, that's something you could reach out to us, and we can help you size up for your building and application. And two other questions that came in were local law related. So the first question was if New York City local law, or is local law 97 specific to New York City? So the answer to that is yes. It is not statewide. However, I would imagine there will be requirements eventually. Often New York City kind of paves the way and the state follows. Another question was whether or not panel radiators would be good for to achieve higher delta T's. I believe the answer to that is yes.
That's correct. Yep, that's correct. Actually, my wife and I, when we moved up to New Hampshire, we bought a home that had a forced hot air heating system, and we added on to the house, put a second story on it, and we put in panel radiators throughout the house. So we got about 15 panel radiators. The entire system is operating off a single pump, and on out to a reset. So, in the winter time, when bedrooms that are not in use, we basically have the panel radiator off, or we basically have it on a snowflake setting. So it basically allows some flow when a room were to get very cold, but other rooms that we have in use, you basically set it up where what your comfort level is, and it really puts the entire heating system on cruise control. And that's really how in Germany and in Western Europe, how they were able to comply with those strict requirements, with those lower temperature, the new heat requirements by they increased the insulating value of the building envelope, and then they put the panel radiators, typically you put them underneath the windows, those areas where you have your major heat loss, to compensate for the negative draft temperature effect of the window, and then put nice, the beauty of a panel radiator, it provides both convective as well as radiative heat, and they're very easily controlled as well, and they're available in a wide range of sizes.
Right on. So it's pretty much all the questions that I see here. So I appreciate everyone that came in and joined us. Like I mentioned, we'll be getting you your certificates as soon as possible. And Dr. Liu, we really appreciate all the time and effort you've put into this. So not everyone's aware of. I don't know if anyone here has done webinars as well, but there's a lot of time and effort that goes into preparing the presentation, as well as just making sure on a technical level that we're prepared to get it all up and running. So again, Dr. Liu, really appreciate you spending the time with us to give us this presentation.
Nope. My pleasure, Greg, and we want to thank everybody for participating, and hope you all learned something from the presentation.
Great. All right, guys. So that's going to be it. Like I said, you can find this presentation on YouTube, and reach out to us, reach out to our support team if you have any other questions, you want a little follow-up. But other than that, enjoy your Wednesday, enjoy the rest of your week, and take care, everyone. See you next time.
Yep. Bye-bye.
Bye-bye.
Thanks, Lou.
Yep, thanks.